Hello all and welcome to my YouTube channel. So today in this particular video, we are going to talk about how to fine tune Llama 2 model, and also we are going to talk about what is LoRA, and we are going to just understand why this LoRA is required, and we're also going to understand what is quantization and how it is helpful in fine tuning the Llama 2 kind of models, right? So this is the whole agenda that we're going to cover in this particular video. So let's get started. The first thing, before we start with this particular tutorial, I just wanted to make you understand about the fine tuning steps that we are going to progress in this particular video. But before fine tuning, we should also understand why the fine tuning is required in such generative models. So essentially, let's start with some examples. And let's say you're working in a medical domain and you want to extract some information, or you want to generate some informations based out of your domain knowledge that you wanted to interact with the generative models. And when once you start interacting with the particular model, let's say you start prompting and you start giving the context and you start giving it to the model, and then the model is unable to understand the domain that you're talking about. So maybe the language that you're using for a medical domain would not be captured in the knowledge base of a particular model, so hence it won't be able to give you best answers that you require for your specific domain. And that's where the requirement of fine tuning comes into play. And by the way, when you try to do prompting and wanted to extract some information by using the prompting, and when you're trying to play out with some prompting to make your model understandable about your particular data, that particular information or that particular step is called in context learning. So in context learning is generally when you're trying to do a prompting steps. You're trying to play with different prompts to extract better output from your model. So that particular step is known as in contextual learning, and you're trying to understand, you're trying to extract the information from the knowledge base of a particular model. So that is what in contextual learning means. We are not learning anything, but we are trying to play with some prompts to understand or to extract the knowledge base from the model to get the right result out of it, right? So this is the in contextual learning, and the first step always it should be like you should take up the already existing model. You should try to do an in contextual learning. That is, you are going to try out some prompts and play with some prompts and just understand like whether that particular model is suitable for you or not. And once you get certain output, and based on those certain output and based on those certain prompts, you decide that okay, this model is unable to understand the language that I wanted to understand. So maybe you can now think about fine tuning the generative models. So I think this is very clear for you. So now let's understand why this fine tuning would be helpful for your case. So whenever you see that the domain is a challenge for a particular model, so you can start fine tune that particular model to understand your own language of your domain. So in this case, when you see a medical domain, so medical domain might have some technical names, so that majority of the models won't be able to cover that. So you specifically need a model that can be able to understand the language that you are working with. So if it is the medical domain, then you should fine tune that particular model based on the medical domain, right? So that's the need of fine tuning a particular generative model to update the knowledge of a particular model. Okay, so with that understanding, we can move ahead to understand how the process of fine tuning will look like in this particular tutorial specifically, because there are multiple steps are involved in achieving a good fine tuned results when you see a chat GPT kind of model. So if you want to get into that stage, we might have to include multiple things when we are trying to say that when we are trying to fine tune a particular model. But let's speak about this in particular description. Okay, so if you can see on the screen, there's an overview of SFFT and RLHF. So SFFT is nothing but supervised fine tuning method, and RLHF is nothing but reinforcement learning human feedback. So these are the two steps that has been generally applied in training the ChatGPT models. So first initial step of any of the model before even fine tuning, we generally have to pre-train the particular model on a specific domain. So if you see that particular this particular image, on this particular image, if you see, there is some pre-trained data that is available, and then you take that pre-trained data, maybe it could be any of the internet data, maybe Wikipedia or any of your data that is available on the internet. You take that particular data, you try to put into some model and then train it. Based on that particular training, you get a pre-trained model. So now this pre-trained model is able to understand the language that you are trying to make the model understandable, right? So this pre-trained model could be like BERT, it could be GPT model, GPT-1, GPT-2, GPT-3, it could be Flang model, it could be any other generative models or any other natural language processing models. So this pre-trained models and this could be also be llama model. So it has to be first trained on a language, a pre-trained language, so that it can understand the contextual information about it, it can understand the words, it can build embeddings around it, and then that's what the knowledge base of a pre-trained model comes in. So this is the first stage, and then the next stage comes in where we are trying to fine tune it. So once we have this pre-trained model, we're trying to fine tune this on a certain domain. So this is where, let's say, llama 2 is available at the pre-trained model stage, and then we are going to do a supervised fine tuning. So what is happening here is in this supervised fine tuning step, we are trying to take domain data. So let's say we are taking medical domain data, and then we are trying to fine tune it using a Instruct Dataset. So we are trying to make sure that we are trying to prepare this pre-trained model to understand some commands or some instructions by providing it, right? So we have to prepare the data in such format. So essentially, you might have done some kind of classifications or regression problems over this kind of pre-trained model. Might be you have taken the BERT model and you have fine-tuned it to classify some objects, right? But here in this fine-tuning steps, in generative steps, we are trying to modify this training process by giving an instruction data. So we construct a instruction data where it will have an instruction, where it will have a context and also a response, right? So this is where the fine-tuning step becomes different than the classification training or classification fine-tuning. So this process is very important to understand, where we are trying to supervise, fine-tune based on the instruction data set. So let's say we are going to pick up this llama 2, and then we are going to take up a domain data or your specific domain data, and then we are going to prepare that domain specific data into a instruction data, and then we are going to fine-tune that particular llama 2 model, and then we are going to take up an RLHF method where we're gonna take this fine-tuned model and do a human feedback format by using reinforcement learning, so that we can make sure that the model shouldn't hallucinate, the output of a model shouldn't be toxic, and there are other parameters that RLHF method gonna help us to further fine-tune the output of this supervised fine-tuned model. So this is where the whole step of our generative model comes into play when you compare it with ChatGPT. So this is the whole flow a ChatGPT model has followed, and that's why we are able to see this particular steps. And then again, you can do in contextual learning after that. So you can start prompting it once these methods are done. So in this particular tutorial, we are just going to focus on supervised fine-tuning method. We are not going to go ahead after this supervised fine-tuning method, like we are not going to do RHF. But in this tutorial, you're going to get an comprehensive knowledge on what is supervised fine-tuning and how we can construct a dataset, instruction dataset, and then how you can fine-tune a llama 2, right? So this was a kind of an overview. Obviously, there are multiple details available. I will go through the some details of it, like what are the important information that you need to consume before doing a supervised fine-tuning, right? So let's go ahead with this particular thing. So essentially, you have to install some of the dependencies. So I'm installing bits and bytes transformer. I'm also using PEFT. So PEFT is a parameter efficient fine-tuning library available from transformers. You can use it to quantize your models, to make your model very efficient while training. So I will talk about it, and LoRA is one of the PEFT method that you can use it, and then we can also use accelerate, and then we are also going to use TRL library, which is very very good library, I should say, for fine tuning your generative models. So it has it has all the dependencies, all the capabilities available to supervise fine tune and also perform a reinforcement learning fine tuning. So this TRL library is very helpful. You can take a look onto its GitHub page, right? So we are going to use all of these dependencies for this particular fine tuning, right? So right now these are the imports that I'm doing, and I'm going to load the data set which has dialogue of a person conversations. So there are different persons who are doing a conversation between them. So we are taking that particular data set with a dialogue, and we are going to take a summary of that particular conversation that happened between the different persons. So this is what we are trying to do in this particular tutorial. We are going to take the dialogue of those persons and we are going to do a summary of it. So we ask the model to generate a summary for the conversation that has happened between the two persons or three persons. So this is the data set that we are going to use to summarize or fine tune the model to summarize the conversation, right? So this is what we are going to do. So we are going to load this particular data from the Hugging Face, and then you can see there are some number of rows and number of columns available from this particular data set. Now we're going to prepare this particular data into Instruct Dataset, right? I talked about it, right? So you have to prepare this dataset into a Instruct Dataset so that you can train your generative model, right? So this is what I'm going to do here. So you can see I have to put this dialogues and summary in this format where this becomes the summarize the following conversation becomes your instructions, and this particular dialogues becomes your kind of an input, and then this summary output, which is the summary of this particular conversation, becomes your as a response, right? Or it becomes your summary. So this is the data set. This is the format that I'm going to prepare, and to prepare this format I have prepared a function which is kind of called format instructions, which is something like this. It takes in an instruction, and then I give an instruction like summarize the following, and then I also give an input tag, and then below the input tag I give all the dialogues that has happened for that particular conversation, and then also pass in the summary. So that's how this function is helpful to prepare this data. And then also I'm going to use another function which is an overlap for this particular function. So it will prepare this particular dialogue summary and format this particular dialogue and summary into a certain Instruct dataset that I have given here, right? And I will store it in the text key. So all the instructions, all the Instruct dataset that I want to prepare will be stored in this text key. So this particular function will return the dictionary output where it will have dialogue, summary, and the Instruct dataset prepared. Now we are going to process the dataset by using this process dataset function. It will just randomly tuple the dataset and also apply the generate instruction dataset to each of the row for this particular data, right? And we're going to also remove the ID and topic column, which is not required for our use case. So we're just getting rid of it. So that's the functions that I'm going to use. So now we have to apply all of this steps. So I'm going to take up the dataset and I'm going to apply all of this into the dataset. And then we are going to select some rows. So we are going to take 500 rows from the train dataset, and we are going to take 50 samples from the test dataset and validation. So this is how the dataset will be. So after the pre-processing steps applied and such dataset created, we have these three columns available: dialogue, summary, and text. So for training we have 500 data, and for testing and validation we have 50 data. So that's the pre-processing step that you can do. Now if you want to visualize this, you can visualize this particular output of particular text, how this looks like. So once we have this dataset prepared and we have the Instruct dataset prepared, so what we can do is we can start downloading the model. So before we start downloading the model, we have to focus on what type of model we are using. So here you can see I'm using LLAMA2 7 billion parameter model. It is not chat model that I'm using. There is also a LLAMA2 chat 7 billion parameter model. So in this use case, we are not using chat model because we want to take up the base model and then we have to fine tune it on that particular model, right? So That's why we are taking this 7 billion normal base 7 billion parameter model. And you could also try with other versions of llama 2. I specifically chose the 7 billion parameter because it could be helpful to train here in this collab environment. So I chose 7 billion parameter model. And also I'm using bits and byte configuration method, so it is helping me to load this particular 7 billion parameter model in a quantized format. So I'm using like load in 4-bit format to quantize it. So specifically it's gonna if you see the model, it could be like 28 GB of model, 7 billion parameter model. It could be like some 28 GB model. So if you load it in 4 bits of model, so you can fit that particular whole model into a 5 GB of RAM. So that's why this bits and byte configuration are helpful to reduce the size of the particular model from huge size, from its base size to the quantized size, which is 5 GB of model. And then you can use this quantized weight to fine tune your model, right? So obviously you're gonna get a little reduction in the accuracy because obviously you're trying to reduce the floating points and you're trying to quantize it into certain number. So that is a trade-off that we should accept when we're trying to fine tune a particular model with a limited resource. And if you have huge resource, if you have a huge number of GPU or RAMs, then you can utilize whole 7 billion parameter, and it will take a longer time to train because you have to update all the parameters, right? So that's the need. So because of that, we are using bits and byte configurations, which is helpful to quantize the base model into a limited resource, and we are trying to fit that particular model into a limited resource of GPU. And that's what we are trying to do here. And then we are going to use auto model for causal ML because llama 2 is a generative model, so it's a causal ML model. And then we are going to pass it into the model ID, and then we are going to pass in the bits and byte configurations so that we load the model in a quantized format, and then that's how the model is getting loaded. And we are also going to take up the tokenizer, and then we are going to pad the tokens on the right side. And then also we are going to add the end sequence token to the particular tokenizer, which is very important for this llama 2, so that it stops generating whenever that particular end of token is achieved, right? So these are the important things that you have to start with. So remember, we are not loading the whole or the bigger base model. We are trying to take the base model and we are trying to quantize it, and then we are going to use that quantized model, quantized llama 2 7 billion parameter model for our fine tuning, right? So with that particular model, I just tried to do a zero-shot inferencing. So this is where your in-contextual learning is coming to play. I just tried it for the first only for one prompt. You can try for another prompts, but I just gave a simple prompt like summarize the following conversation, and I passed the dialogue from the data set that we have, and try to see what is the output that we are seeing before fine tuning. So this is a base model that we are going to see. So since this is a base model, which is not a chat model, so this base model is kind of a generative model. So it will just see the previous token and it will try to generate a new text out of it, right? So it's not a chat model there where you're gonna give instructions and then it will give you an answer based on that instruction. If you have to get that particular thing, then you have to use chat model. But this is a very base model. It doesn't have capability of understanding your instructions. So hence this particular output will be something like this. If you see, it's almost the same output that you're getting as an input, something like this. It's trying to complete the conversation that he had. So if you see at the top, this is the baseline human summary. This is the actual summary that is required, that is given by this particular conversations in the data set. And then this is a model generated output, model generated summary. So you can see it's not fairly doing very good in generating because it's not a chat model, and it doesn't have capability of understanding the instructions, right? So now, with this information, you have the quantized model, you tested it on some prompts, and you know that the prompts are not working because it's a base model. Now what? Now you have to fine tune this particular model, right? But for fine tune this particular model, if you fine tune this particular model, you need to fine tune it. If you try to fine tune it from the base model, then you need to fine tune all the parameters, right? And there are billions of parameters, like 7 billion parameters you have to fine tune. And that is not possible with the particular RAM that you have, with the particular GPU RAM we have. it might go and out of memory. So with that thing in mind, there is a concept called LoRA, which is low rank adaptation. What it is doing is, instead of fine tuning all your 7 billion parameter model, you just have to fine tune some of the parameters of a particular model, and that can help you to fine tune a model based on some parameter modification, not all 7 billion parameter modifications. So that is the concept behind the LoRA. So what it is doing is, you are choosing some of the parameters, not all parameters. You are choosing some of the parameters of a particular model, and you're trying to create a matrix, a similar kind of a similar shape of a matrix of the parameter that you're trying to target, and then you're trying to decompose that particular shape into a different low rank matrix, and then you're trying to train that additional matrix that you have created, a similar kind of matrix, and then finally you're trying to use that particular matrix that you have created and then save it in a particular format, right? And this particular thing, what we call creation of a similar matrix for a same parameter, is called adapters. So if you see this image, this is the let's say a matrix, and then it has a weight, right? So let's say if you have heard about if you're talking about transform model, let's say this is a key matrix. We have query key value, right, in transformers. So let's say this is a query matrix, and then for this query matrix, if you're trying to fine tune it directly, then you might have to fine tune all the query key and value matrix, right? But in this situation in LoRA, what it says is, you don't have to fine tune all the parameters. You can choose a particular parameter. So I'm choosing a single parameter which is called query, and then that query is nothing but a matrix, right? So what I'm trying to do is, with this LoRA will create a similar matrix which is A and B, and if you multiply this A and B matrix, it will have a similar shape of this the original matrix. So in the parallel, you're trying to create a similar matrix with the same shape but in a decomposed form, right? So that's why it's low rank adaptations, which is trying to take a similar shape of a matrix but in a decomposed form with certain rank. Rank means a certain number of rows or columns, right? So now you have this original matrix, and also you have parallelly created a similar kind of matrix or similar shape of a matrix in a decomposed format with certain rank. And now what you're trying to do is, you're not trying to fine tune this matrix, the original matrix. You're trying to fine tune this matrix, this matrix that you have created. And then once you have fine tuned this particular matrix, by the way, this is also known as adapter. And then once you have fine tuned this particular matrix, you try to merge this change with the original matrix. So that's the learning that you did. You had the initial learning weights, and now you wanted to learn a new information, right? So you created a new matrix with the same shape. You learned these parameters, and then you merged it here with the same matrix, and then you get a new matrix here, the same new query matrix. So this is what happening at each and every parameter that you're trying to target. So this I explained with the query. You can also apply with a value matrix. You can also apply with a key matrix, right? So this is what LoRA is all about. And if you see this particular parameter are very less, because you're choosing a particular parameter and you're trying to fine tune that particular parameter, and then you're trying to merge with the original weights, and that's how the fine tune model comes into play. So if you see this diagram at the bottom, you see there is a pre-trained weights that are already pre-trained by the particular model, and then we created with the LoRA, we created a new matrix for the certain parameter, and then we are trying to fine tune this matrix, the newly created matrix, and then we're trying to merge with this pre-trained weights, and then we're gonna get a new matrix here. So this is what it's being explained here. So during the training, this is happening, and after merging, we're gonna get this. You can see this is the merged weight. You're gonna merge these two, and then you're gonna get a merged weight, which is gonna be a different fine-tuned weights after training. So this is a comparison that I wanted to show you, the need of LoRA and how the LoRA is actually working at the back end, right? And now with this information, I think now it will be very helpful to understand what is happening here in the upcoming text. So remember, we had taken an Instruct Dataset, we prepared it, and then we have a quantized model, right? And we saw that the quantized model is the quantized base model is unable to understand the instruction data. Now Once we understood this LoRA concept, now we are going to apply this LoRA concept. So this is a function that will help us to understand how many parameters that we are going to fine tune. So this function is helpful function, so that you can understand how many parameters that we are going to fine tune this particular fine tuning step, right? So the first step begins here is we want to import prepare a model for K-bit training from the PEFT. So you have to enable your gradient checkpoint, and then also you have to prepare your model for K-bit training, and then you have to pass in the imported model or the loaded model from the Hugging Face, and then you have to pass into this the prepare model K-bit training, and that's how the model is ready for K-bit training. And then I have printed this particular model, this the LLAMA2 model. So you can see these are the parameters you see, and in this parameter models, if you see, this is self attention layer, right? This is LLAMA attention, right? And this is where the transformer layer is coming in. This whole LLAMA module has a transformer layer, right? So you can see this is LLAMA attention, and then we have this query, key, value, and there are some other projections available, and then rotatory embeddings. So you can fine tune all of these layers, but since we have talked about the concept called LoRA, so we don't have to focus on on training on all the parameters. We are just focusing on the query, key, value, and other projections, which is these are the four metrics that we are going to focus. And with this, in these four metrics, we are going to apply LoRA, which is we are additionally going to create a similar metrics for each of these query, key, value metrics in a different metric space with the same dimension size in a decomposed format using LoRA. And we'll have each of them, and for each of them we're going to create it using LoRA, and we're going to fine tune all of those embedding, and then finally we want to merge that fine tune weights into this original weights. So I hope it is making sense to you. And by the way, you can see there are like 32 layers of this attention layer inside this LLAMA2 layer. So we are going to use we're going to focus on this query, key, value projection, and other projections, right? So this is what we're going to apply. So if from the PEFT library, you're going to import LoRA config and get PEFT model. So in the LoRA config, you have to mention the rank, like what is the rank of this particular matrix would be, the dimension, and the LoRA alpha is how many decomposition you wanted to make. So it can be different. You can also change these parameters and try it, and you can try and test it. And the next module is something like what is the module that we're going to focus. So that is what I was talking about. Like we are going to target about the query, key, value, and other projections. So this is the module that we're going to target in the model specific. So in the LLAMA specific models, this is a target module name. So you have to write it up here. And let's suppose if you're trying to fine tune Plan T5, then query, key, value is your target module. It will become your target model. You have to open your model and search which are the target models and search inside the model. That is, you want to focus on the model, and then you can fill it over here. So that's the focus. So in this particular format, we are going to focus on query, key, value, and other projections, which is so these four metrics. For these four metrics, we are going to create an additional metrics in decomposed format, and then we are going to fine tune those metrics, and then finally append it into the original weights, right? And then we are going to mention this LoRA dropout, and then you can also mention some bias, which is kind of, you want to have some bias. You can fine tune it on the bias also, but I'm not choosing to fine tune it. Maybe you can refer LoRA config documentation to understand. And the task type is causal LM. So because we are using causal model, so you have to specify causal LM. So let's suppose if you are using Plan T model, which is a sequence to sequence model, so you have to change the task type to sequence type. And that's how the LoRA config is ready. And now you have to pass this particular quantized LLAMA2 model that you imported into the get PEFT model, and with your LoRA config. So this step is essentially creating the additional metric for all of these target modules. And once you have created this particular additional metrics inside your model, and then that is what we call an adapter. Adapter has been created. Additional adapter. That is a terminology that is being used, so you can understand with the terminology. And now you can use the method called the function called print trainable parameters, and then it will help to understand how many parameters are trainable. So if you see, there are like you can see there are millions of parameters available, right? And then you are just training like 0.47% of the training, right? 0.47 is very less compared to the percentage that we have. And you can see the trainable parameters. So it's very less number of parameters that you are training, and you can expect like the weights should be very less, and you're going to get a better performance even by training this small less amount of parameters. And that's the beauty of this LoRa training. And that is why you have to use this LoRa to make your fine tuning very efficient, and also very less hardware consumable, right? So this is the beauty of this particular PEFT module with LoRa adapters, right? So once you have this quantized model and with LoRa config initialized, all your additional weights ready with model training, so you have this model setup ready. Now you can proceed with the training part. So you have the Instruct dataset, you have LoRa models, and then you are now trying to train this particular model, right? So for training, I am scheduling a tensor board for better visualization of training loss and validation loss. So now the next step goes on here is to import the training argument. So you can mention your training arguments that are being used, and you can see that I'm using a different kind of Adam optimizer, which is paged Adam optimizer. And this is a special type of optimizer that has been released for training of the generative AI model, because Adam also stores some of its variables or some of its additional weights in the RAM or in the GPU RAM. So this paged Adam W is generally trying to use the CPU memory also to optimize the learning and store the optimizer weights. So that's a different kind of Adam optimizer that you can use for your own training custom generative models. And then you can play up with these parameters. I am using specifically learning schedule as cosine, and then you can play with these particular parameters. You can also mention this config use cache equal to false to avoid some warnings. And then finally, we are going to use TRL library. And then from here, we are going to import SFTT trainer, which is supervised fine tune trainer from the SFT from the TRL library. And this is very useful class that has been given from the TRL, and it is very handful, which reduce a lot of the plate codes that are available to do before going to train the model. So you can see we just prepared the instruct data set. You did the you initialize the LoRa config, and then you finally jumped into the training part by using this SFT trainer. So in this SFT trainer, you have to mention the LoRa model, the LoRa PEFT model, and then you have to specify the training data, the validation data, which is nothing but the instruct data set, right? So you're going to pass in the instruct data set, and then you also pass in the LoRa config, and then you're going to pass in the field where the instruct data set is available inside this data. So remember in the text key we have this all the instruct data set, right? And then you have to mention the max sequence lengths. I took 1024. You can take it up to 4096 because that is the maximum sequence length of a llama 2. And then you have to specify the tokenizer, and then you have to specify the training arguments that you have taken up here, right? So that's the step that you have to mention inside this SFT trainer, and then you have to just run trainer.train command, and that's how you're going to train the particular model on your own data set. And you can see it ran for like 20 minutes per epoch, and and it has trained quite a lot for 2 epochs. And then I tracked it using TensorFlow board, and if you see the loss, this is a training epoch, and this is a learning rate, and this is a training loss. You can see that loss is going downwards for the training, right? So that's how also you can take a watch on your training and testing. So after like half an hour of training for 2 epochs, because I had just a limited data set, so I used the limited data set to fine tune it in a small amount of time. So this is what I used, and I train it. Maybe you can train for longer time for better efficiency. And now once you have trained the model, now what you can do is you can save the particular model. So if you when you're gonna save this particular model, right, it's not gonna save the base model and the additional adapter weights, the LoRa weights that you have created. It's not gonna save both of them. It's just gonna save only the adapter weights. That is the LoRa additional weight that you have created. So it's gonna save only those. So if you see, I'm just saving. I'm just trying to save this particular model with only the additional weights, the adapter weights. So whenever I try to save this particular model, right, you can see additional files are being created, which is called tokenizer config, obviously, and there are some special token map and tokenizer.json, and also there is some adapter .json files are also created, which is specifically storing the weights, trained weights of the LoRa config. So if I have to tell you that what is it, so these are additional weights that has been gone trained, right? So these are additional weight that is just being stored when you try to save the model. And now if you want to use it for inferencing, right? So how you can use the additional adapter weights, because uh, once the model has been trained and you saved that particular model, it's not saving the whole model, it's just saving the adapter weights. So how you can use it for inferencing? So that's the beauty of this LoRa. And what you can do is you can import PEFT model from PEFT. You can import auto PEFT model causal LM, and you can also import auto tokenizer, and then you have to mention the directory of the adapter weights where you have saved it. And then in this class you have to pass in the directory of this, and then you can put up all the parameters that are required in it, and you can just import this, and you can just initiate this particular cell so that it will start downloading the base model, associate it with your adapter model, and also add it. It will merge it into this particular pre-trained base model. That's what it is doing here. It is trying to take up your adapter weights, and internally it is also trying to load up your base model and trying to merge it with your original weights, original base weights, and that's how you're going to get a train model. And then you're also going to load up the tokenizer, and that's ready. You can start doing an inferencing. So I, for inferencing, I took the same example, and I use the test data set, and I'm picking only the first row of the data set, and I'm prompting with the same instruct data set that I use the prompt, right? I use the same prompt in the instruct data set. So I'm giving the same, but this time not giving the summary. I'm just giving a dialogue what I have, and I'm trying to get the summary out of it. So I just initiated the trained model and tried to generate the output from the trained model, and that's how it generated. And now let's see what is the output. So this is the input prompt, and this is the instruction. And if you see, this is the input, these are dialogues, and this is the human summary that is available, right? This is a human summary that the dataset has, and this is the ground truth, and this is a trained model generated text. If you see, this is the model has generated the summary out of it. I can see it is doing fairly good if you read this particular summary. And likewise, you can fine tune this particular model for other use cases, and you can generate comparison between baseline and the model generated text, right? So that's very important thing. And and I will also speak upon something which is very important. Like, let's say you have one task of, let's say you did the task of summarization of the text, right? Now you wanted to do a different task. Let's say you want to do a translation task. You want to translate something, right? But you're going to use llama model itself to fine tune it. So in the production, you cannot use like you can use, but it is very difficult to use the same compressed format, right? The compressed or the merged data or the merged weights from the base model. So let's suppose you're trained a summary model, and then you merge it with the base model, and you're trying to load it into the server, right? And then you have a similar use case, but this time you want to do a translation with the same base model like llama model. So what you're going to do is, generally what you will do is, you're going to take the base model, and then you're going to train an adapter model for translation, and then you're going to merge it, and then you're going to serve it into the server, right? But with using this LoRa, what you can do is, you can train these different adapters. So you can have a summary adapter, a different trained summary adapter, like what we had here, and then you can train a translation adapter. And then what you do is, these adapters will be in, like, in megabytes, like in 10 megabytes or 5 megabytes. It will be very small size. So what you can do is, you can just place a base model of Llama 2 in your main repository in the server. And then as per the requirement of translation, or as the summary, you can merge your adapters as per the requirements of your task. So let's say if you have summary requirement, summarization of requirements, so you can merge the summary adapter with your base model, and then you can do a summarization task. And let's say if you have translation task, what you can do is, you can use your translation adapter. You can plug in with your base model. So the efficiency becomes very great here, because you're not trying to import whole base model again and again for different tasks. You're just keeping a same base model available in your RAM, and just you're going to import and merge your adapters for your different tasks that you have trained. And that's the beauty of this particular LoRa model. And that's why we are very fond of training the generative model by using this QLoRA and LoRa optimizations. And that is very remarkable benchmark that we are able to witness in this training of generative AI. So I hope this makes some sense of out of it, and maybe you can utilize it for your use case. So once you have done the inferencing, and then what you can do is, you can take up this trained model, and then you can merge it, and then you can push it to the repository, or you can push it to the Hugging Face hub. So that's the part of it, and I think This is the whole tutorial that I wanted to make. And I think if you wanted to train some of your custom model on your own data set, then you can use this approach and try to work on building Instruct dataset, and then trying to fine tune the model on this particular by using the LoRa approach. So if you have any questions around the training part, please mention in the comments, and I would be happy to help on you that. And hopefully you enjoyed this particular tutorial. Thank you.